Okay, so we're going to go with question 4.5 today. So 0.25 kilograms of steam at 1 megapascal and 400 degrees Celsius is initially filled inside a piston cylinder device made with a set of stops. And the location of the stops corresponds to 55% of the initial volume. Now the steam is cooled. Determine the compression work if the final state is A, 1 megapascal and 250 Celsius, or B, 500 kilopascals. Okay, and also find the temperature at the final state in part B. So this is the first question we're doing that has stops. So I'll just draw that out in case it's difficult to see, but you have a piston cylinder. So here's sort of the piston itself. And normally as we add heat or do heat or work the system, this piston will move up and down. However, we're being told that there's these sort of like stops right here. So the piston can only move this far down. It can't go beyond that. Significance of that is like, because work is in a constant volume process, like a constant pressure process, like a piston cylinder, work is just P times the change in volume. Now, if we start we can only do so much work is the point I'm getting at, because eventually we hit this sort of dashed line. And if we continue trying to do work on the system and compress it further, we won't be able to. So there's only so much work we can do. If we're talking about it doing work, as in the piston moving up, well, then you can go as far as you want, at least as long as the piston is still big enough, but you don't have the same constraint as you do on the way down. Now, just again, as a note, we're being told two states, right? We're told that this corresponds, this region here corresponds to 55% of the initial volume, but we're not told that we actually get to the stops. We're just told two different states. So we're going to see if we actually reach those stops or not, right? So if we ever find that our volume calculated or found from the tables is less than 55%, we're going to brute force it to being 55%. Okay? Because we know it can't go less than that. So let's go get rid of that. And get rid of that. Good. All right. So let's just check the numbers again. 0.25 kilograms, 1 megapascal, and 400 Celsius. And we're told steam, so we can go straight to the steam tables. Okay, and I'm just going to open this up on my other screen. Okay, let's go to the steam tables. There we go. Okay, so we're looking for 1 megapascal, 400 Celsius. We're looking for this line here. Now what we're interested in is the volume that's going to be. For now, we're interested in that. We're also, well, the pressure we know is 1, and it's going to be constant until we hit the stops, if we hit the stops. But right now we care about the specific volume, and we can see that at this state, the specific volume is 0.3066 meters cubed per kilogram. Oops. So it's 0. Goodness. So V1 being the specific volume is 0.3066 meters cubed per kilogram. And we have 0.25 kilograms, we're told, right? So if we multiply this by 0.25, we see the actual volume, which I'll denote with a strike through there, like this last time. The actual volume times 0.25 kilograms. So let me just do that quick. And I'm getting a value of 0.07665. 0.07665 cubic meters. All right. So that's that. Now let's find the specific volume at state 2. Now we're given two cases of what state 2 can be. So let's see in part A of the question what they're asking. In part A of the question, state 2 is at 1 megapascal and 250 degrees Celsius. So it might or might not be a steam or not, but just judging from those parameters of 1 megapascal and 250, I think it's going to be a steam. So I'm going to start with the steam table. So let's go here. 1 megapascal, 250. Yes, we're still a steam for now because we have an entry at 1 megapascal and 250. And again, we're looking here at the specific volume, 0.2327. All right, meters cubed per kilogram, 0.2327. So V2, 0.2327 meters cubed per kilogram. And again, multiplying that by 0.25 to get the actual volume. It's going to be 0.058175 meters cubed per kilogram. That should be a 0. It looks a bit like a 6. All right. So that's our change in volume. And now, like we said, we know the minimum volume we can have is 55%. So this guy here can only be 55% of this guy here, right? So we can just see from inspection, it's like 0.058 out of point. Well, we can just do the math to be safe, but we're sure that this is above 55. So 0.058175 divided by 0.07665 times 100, it's 75%, and well above 55%. We are okay to assume that all of this consists of work done. Now, again, like I said before, if we found that this was less than 55%, we know that the volume can only go to a minimum of 55%. So we can only, let's say, take credit for the first 55% of that volume being reduced to consider that as work. All right, but in this case, we haven't hit the stop, so it's basically, you can almost pretend they're not there for this case, for part A anyway. Okie dokie. So we want to find the work done, I believe. So the work done for a constant pressure process like a piston is just P. We've seen the integral enough times already. P V2 minus V1. We know P is 1 megapascal. So 1 times 10 to the 6 pascals. V2 minus V1 is 0.058175 minus 0.07665. We do this, what are we going to get? Let's see, 1 times 10 to the 6. 58175 and 7665. So I'm getting my minus 18.475 kilojoules of work done in the first case. Okay, and again, let's just cross-check the validity of this sort of outcome. So we have a negative number. Does it make sense that we have a negative number? Well, that means work was done to the system. We had to input work to the system to compress it, and clearly we did. All right, so we're at minus 18.475 kilojoules. We had to use 18.475 kilojoules of our own to get it going from state 1 to 2. All right, so that's the first part. I'm going to box this because this part B is basically saying forget the state that was asked in part A. We're going to pretend state 2 is something else. And what is that something else? Let's see. That something else. Okay, 500 kilopascals. The final state is 500 kilopascals. Okie dokie. So clearly, if the final state is 500 kilopascals, what that means is that it's no longer a constant pressure process, right? Because we're starting at 1,000, we're going to 500. But how can we do that in a piston cylinder system? Well, the way we can do that in a piston cylinder system is if we start taking away, cooling it or doing work or compressing it, and then we hit these stops and we continue cooling it, we're going to lose pressure, right? So maybe we hit the stops in this case, but let's see. So the thing is, of course, that is pretty much the only way that can really happen. So immediately we know that the volume of the cylinder is now only 55% of the initial, because remember, like we said, we have these stops here. Everything below the stops, basically when the piston comes to rest here, everything here is 55% of what it was before. And only once we hit these stops does the pressure start changing if we then continue to heat it, cool it or heat it. Well, in this case, cool it. So we know we've hit these stops. We actually know the volume. And we know also that once we hit these stops, we can't do any work because the volume isn't going to change unless we start, heating things up and increasing the pressure and eventually lifting this up. So what does that mean? Well, the work done is just the change in volume at the pressure that change occurs at. So yes, eventually the pressure will change, but that's not well after, that's after the volume stops changing at a constant pressure. So we can still thankfully use the equation here at the same pressure, but now we know that V2 is going to be only 0.55 of V1. So we can either do it sort of explicitly using V1. Well, actually, let's do it that way. So work equals the pressure. So 1 times 10 to the 6. Now, yes, I know the pressure eventually gets to 500 kilopascals, but I also know that only happens once all the work that can be done is done, because all the volume change that can be accomplished is accomplished. The pressure does not decrease until we have hit the stops, until all the work has been done. So the work as it's being done is being done at a pressure still of 1 times 10 to the 6. Okay, and V2 is just 0.55 of V1 minus V1 itself. So we can just more cleanly express that as 0.55 minus 1 V1. Anyways, if we calculate this, let's see what we get. I'm getting minus 34.4925 kilojoules. Okay, so this is how much work we've done, and it's also how much work you can possibly do given the initial state we started in, and given that there are stops that block off the last 55% of the volume. Now the question asks, what's the temperature at this state, right? At the final state. So we know that what's happening, we cool this down, the piston stops, and eventually the piston stops, and that's how much work we're doing. But then we continue to cool it. And as we cool it, the pressure drops as much as 500 kilopascals. So what's happening at 500 kilopascals? Well, we know the specific volume, don't we? We're like trying to identify the state here. We know the pressure, we'll call it pressure 2, is 500 kilopascals. Okay, what's the specific volume? Well, we know the volume and we know the mass is still 0.25 kilograms. So the specific volume is equal to 0.55 of the initial volume, because that's what volume 2 is, divided by 0.25 kilograms, right? So let's see what that is. 0.55 times 0.07665 divided by 0.25. It's 0.16863, 0.16863 meters cubed per kilogram. So let's see if we can find the temperature associated with this here state. So let's see, is this going to be a mixture, a superheated vapor? I don't know. Let's start with the superheated vapor and see if that works. So if we go to the superheated tables and we look for 0.5 megapascals, let's see what the minimum specific volume. So we see at saturation already the specific volume is way too high. So we're not a superheated vapor. So we must be a mixture. So let's go to the mixture tables for water. And let's again look. Here we are. At 0.5 megapascals for water. This line here, let's see what we have. So we have VF and VG is the third and fourth columns. Are we contained within those? I mean, we should be, because we're definitely not a superheated vapor. And sure enough, our value lies between these two. So we know that we're a mixture, right? And of course, by virtue of being a mixture, our temperature is the saturation temperature, which here is 151.86. And that's the answer to this one. So T2 equals 151.86 degrees Celsius.